Good morning, everyone. Hope all is well. Hope everyone is doing all right. Good morning. All right, so you guys had a great weekend. Today we're going to get into chapter 4. Check something real quick. Okay, sir. I don't know if you want to talk to me about that later or most definitely. Just trying to see something real quick. 155. All right. Okay. We talked about this is just me re-emphasizing to my last class, the things that you guys are held responsible for. We talked about this last class, so we don't have to rehash that. But we're going to start here, 4.1, scatter diagrams and correlation. So scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Let me make it a little bigger. Each individual in the data set is represented by a point. As always, give you guys a chance to write the stuff out. So when doing and plotting our scatter diagrams, we'll have two types of variables, your explanatory variable and your response variable. Talk about the difference between the two in a second. All right, so let's look at the difference between the two. Your explanatory variable, it's pretty much in the wording. It explains the value of the response variable, and the response variable is explained by the explanatory variable. In other words, responds to the explanatory variable. And you'll see an example of what that means in a second. And now if you go back to your Cartesian coordinate plane back into algebra, your explanatory variable is going to be your horizontal axis. So in other words, your x variable. Your response variable will be your y-axis, your vertical axis or your y variable. And so that's your domain versus your range, input versus your output. So the explanatory variable is the value we're going to plug into the equation. Response variable will be the one that we get out. Explanatory is independent. Response variable depends on your explanatory variable. And I already mentioned the horizontal and vertical axes. And then finally, your explanatory variable is the predictor, and your response variable is what you're trying to predict. You predicted. All right, can I scroll up? Yep. Explanatory variable will always be X. Response will always be Y. Here, let's see what my response. Here we go. And then right here is just a general example as to how this is going to look. It's just going to be in your first quadrant. And then you have dots that represent, or points that represent each observation. So everybody done with the, okay. So linear relations is going to be when a line best sums up the shape of the scatter plot. All right, so the first two are examples of linear relations. You see, I drew a red line to show that, a line will best sum up what's going on, the pattern that's going on with our scatter plot dots or points. Now, just because it's not linear does not mean that there is no pattern or no relation at all. See the next two, one is like an arc, and then the other one is maybe a wave. So there is a relationship there. It's just not that it's not a linear one. And then the last one is an example of one that has no relation. And then that's what that statement is down in the purple. Non-linear does not mean no relation, just no linear relation. Can I scroll up? All right, next we're looking at associations. Positive associations is when one value increases, the other one increases. So if you notice down here, as you go from left to right, your pattern goes up. And you always read it from left to right. So as it goes from left to right, if it goes up, it's considered positively associated. And then negatively associated means that when one value increases, the other one goes down or decreases. And so when you read it from left to right, if your pattern goes down, that's considered negative associations. Can I scroll up? All right. So linear correlation coefficient is a measure of strength and direction of the linear relation between two quantitative variables. So we have two different, just like any other time, you have your population and your sample symbols. So your population correlation coefficient is represented by Greek letter rho, kind of look like a P, or if you like baseball, the Philadelphia Phillies P. I don't know if it still does, but I know it used to look like that. Greek letter rho, and then just the lowercase r is your sample correlation coefficient, and that's the one we're going to use. We're going to use r. Mhm. All right, so the same directions that I gave you for your standard deviation and your variance is the same thing that we'll do for your correlation coefficient and your regression line. You want to find app, website, calculator, something of that nature that will help you calculate it. Easycalculation.com will do that for you as well, just like with your standard deviation and variance. You would, and I'll show you, but do type in correlation coefficient in Google and put easy calculation behind it. Then the first website that pop up would be it. Mhm. So once again, not asking you to know how to use the formula here. So make sure you have something reliable that can calculate it for you. Just say it again, because sometimes, people will miss it. All right, can I scroll up? All right, so now we're looking at the properties of the correlation coefficient. It is between -1 and +1 inclusive. So it means it can be 1 or -1, but also the values in between. If R is +1, then a perfect positive linear relation exists. If R is -1, then a perfect negative linear relation exists. right, scrolling up. So the closer R is to positive one, the stronger the evidence of a positive association. The closer R is to negative one, the stronger the evidence of a negative association. If R is close to zero, then little or no evidence exists of a linear relation. So once again, goes back to what we were saying before, R close to zero or no linear relation does not imply no relation, just no linear relation. Then 7, it is a unitless measure of association. Number 8 should be the last one. Yep, 8, it is not resistant, so it is affected by outliers. All right, next we just have a few examples, generic examples of what, R being equal to 1 and how it looks deviating from that 1 and negative and all of this stuff like that. So look at the first 3. That perfect positive linear association would just be a straight line and it's increasing. So going from left to right, it's going up. So that's R equal to 1. Now, as your point starts to spread or deviate from that straight line, it's going to move further and further away from 1. So that's where you're looking at the 0.9 has a little more variation or dispersal of the points. And then 0.4, which is further from that perfect 1, has more spread of your points. And then R equal to -1 would be a straight line going down. And then that same type of relationship between your point spreading will do the same thing as it did with the positive 1. Your points will start to spread away from that line, that straight line, and go closer to 0. And the last 2, when R is close to 0, this one right here, remember it's no linear relation, but there's still a relation there. There's still a pattern there. It's just not a linear pattern. And then here, no pattern at all. So don't forget your correlation coefficient only applies to having a linear relationship. So it cannot tell you or determine if you have a relationship that's nonlinear. All right, can we scroll up? Hold on one second. Let me see if I have this table pulled up. All right, here we go. All right, so the next thing is testing for a linear relation. All right, so step one, we want to determine the absolute value of the correlation coefficient. That's it, step two. Step one, we want to determine the absolute value of the correlation coefficient. Step two, find the critical value from appendix A, table two in appendix A. I meant to put table two in front of that appendix A, but table two, appendix A for the given sample size. And I'll show you where that is in a second. Step three, if the absolute value of the correlation coefficient is greater than the critical value, a linear relation exists between the two variables. Otherwise, no linear relation exists. Give you a chance to copy those instructions and then we'll walk it out. All right. Everybody good? All right, so we want to determine whether a linear relation exists between the club head speed and the distance. So here we have a golfer, and the golfer, is going out hitting balls on the range, and the club head speed refers to the golf club and how fast the head is moving as he swings it. And then you're talking about the distance the ball travels, once he hits the ball. So your explanatory variable is the club head speed, and your distance is the response variable. So your distance, the ball travel, the ball is responding to how fast the club head is moving and going to hit it. So you have your explanatory variable and then your response variable. Everybody doing the black? Okay. So those are your observations. Got 100, 257. So he swung the club head. He swung the golf club head at 100 miles per hour, and the ball traveled 257 yards. So that's what these categories represent. You've got 102, 264, 103, 274, 101, 266, 105, 277, 100, 263, 99, 258, and then 105 is equal to 275. Okay. So the first thing we need to do is find our correlation coefficient. All right. Are we ready to switch to another page? Anybody still copy? All right. So you just go to Google under correlation coefficient easy calculator. All right, I'm about to go back to that page. I'll go back to that page. All right, since I'm here, I'm gonna just go ahead and show you guys. So once again, Google correlation coefficient easy calculator or easy calculation, either one. And the first one is right here. And you can just add rows as you need them. So I'm gonna put in those data values real quick, and then we'll get back to it. I just want to show you how easy it is to use this. Now, if you are doing more than typing in values and hitting enter, then you're doing too much. In other words, if you decide to use another app or a website or something like that, got all these ads up here. All right, those are values, hit enter. And there is our correlation coefficient. Any questions on that? That's all I'm asking you to do as far as calculating the correlation coefficient. Make sure you have something reliable that can do it for you. Also, make sure you're careful with plugging in data values because, you know, this is how we had 275 right there. Let's say if I put 276, I get a totally different number. So even if you're one digit off, it can change everything as far as the value you would get. So always make sure you go through your values and make sure you have calculated correctly, not calculated correctly, input your data values correctly. Because like I said, one digit off will change everything. All right. So let's go back to the notes. It's not about the software. It's actually the formula. The formula itself is that sensitive. Yep. Yeah, the formula itself is that sensitive. All right. I know somebody said they were copying that, so I'll give you guys a chance to finish copying. So you see right there, and I did 3 decimal places because that's what the example did. So MATLAB will let you know. I've seen MATLAB do 4 before as well. So just make sure you pay attention. And they don't always ask for the same thing. So it's not always 3, it's not always 4. A lot of times, they go back and forth. I know they don't do 2 for your correlation coefficient. It's either 3 or 4, but they do make sure you're paying attention. So always make sure you're reading those directions on rounding your decimal values. All right. Are we able to go up? All right. So now we want to take the absolute value of your correlation coefficient. So absolute value, I emphasized it right here. Whenever you take the absolute value of any number, it's just the positive representation of that number. So if you took the absolute value of +3, your result is +3. If you take the absolute value of -3, your result is still going to be +3. So it's the positive representation of that number. Right. So the absolute value of 0.93 is still 0.93, just that they want you to compare the positive representation of your number to your critical value. All right. Scroll up. All right. So find the critical value from table 2 in the appendix. If you go to your e-text, it should be A-2. And I'll pull that up in a second, just giving y'all a chance to write. All right. So first thing we have to ask ourselves, how many observations do we have? If you go back to the chart, now these are not 16 data values. This is one observation. This is the second observation. This is the third observation. So each row is an observation. So you don't count 16 numbers. It's only 8 numbers. So we have 8 observations here. 1, 2, 3, 4, 5, 6, 7, 8. Put that back. So that's why n is equal to 8. And then if you go to the chart, all right, so this is what the chart looks like. This is just a picture from my actual handbook. But in the e-text, it'll look just like this. Like I said, just go to page A-2. So you go to where n is equal to 8. All right. So n is equal to 8 right here. And then you see our critical value is 0.707. If I had 20 observations, go to 20, and then it'd be 0.444. All right, questions on how to read the chart? Let's go back to our notes. So that's why I have 0.707. And now you want to compare the absolute value of the correlation coefficient to the critical value. So absolute value of our correlation coefficient is 0.939. Critical value is 0.707. So absolute value of R is greater than the critical value. And so since the absolute value of our correlation coefficient is greater than the critical value, a linear relation exists between the club head speed and the distance. All right, everybody good? So that's 4-1. Yeah, we got time. We can start on 4-2. We don't have to finish it. Yep. So I say, okay. All right, so yep, that's all 4-2 had. So let's look at least squares regressions. Least squares regression line is the line that minimizes the sum of the squared errors or residuals. So that term is going to come back. We'll use it a little later, errors and residuals. And it's the line that best explains the relationship of the data. All right. Of course, let me know if I scroll up too fast. All right, so finding a regression line. Now, there are two ways that we will be presented or given information, and we'll walk through both of those ways. So if we're given information in pieces, then we'll be using this formula here or these formulas in order to find a regression line. But if they just give you the data set, then you can go to correlation, regression line, easycalculation.com and plug in your data value. So like I said, we'll walk through it. Let's go back down to that last piece. Okay, so finding the regression line, y with that part of a triangle hovering over it. Sometimes it's called a caret, sometimes it's called hat. So, normally we call that y hat. If you have that, like I said, two pieces or two lines of your triangle missing that base, that's considered y hat. Then that's equal to b1x plus b0 or b naught. So now that's going to be your predicted y. Whenever you see y hat, that's your predicted y. Remember I told you that y, your response variable, is what we're going to predict. So the regression line is going to be used to be able to predict future values based on observed values. So then you have B1 is R, which is your correlation coefficient, times S sub Y over S sub X. And you'll see what those represent in a second. Also, that's going to be your slope. So if MATLAB asks you, whatever B1, the value that's sitting in front of X will be your slope. And then B0, so Y bar minus B1 times X bar. That's your y-intercept. All right, so I mentioned R is your correlation coefficient. X bar is the mean of your X values. And I wrote it over here. Don't forget X is your explanatory variable. And then S of X is the standard deviation of your X values. Y bar is the mean of your Y values. And once again, reminding you that Y is your response variable. And then S of Y is your standard deviation of your Y values. All right, are we okay? Scrolling up. So the regression line is used to predict an outcome based on previous observations. So that's what I mentioned to you guys already. All right. So let's use that information, those formulas, to find a regression line. Notice in this type of example, they give us those pieces. So they give us the correlation coefficient, X bar, Y bar, S of X, and Y sub X, S of Y, excuse me. So if they give you those things, then you'll have to use the formulas that we just were presented before you. And so we'll walk it out. So the correlation coefficient here is negative 0.946. X bar, mean of our X values, 4. Y bar, mean of our Y values, 10. S of X, 2.44949. S of Y, 5.612486. These are standard deviations. All right. So first thing we want to do is find B1. Now we have to find B1 first, because if you go back to the formula, remember B1 is a part of B0's formula. So you have to find B1 first. And so all we do is just plug it in accordingly. That's R times S sub Y over S sub X. So you take the numbers they gave you for each one, plug them in properly, negative 0.946 times 5.612486 divided by 2.44949. And we end up getting negative 2.1676. Once again, if MATLAB asks for those numbers specifically, make sure you pay attention to how many decimal values they want. So find B0, Y bar minus B1 times X bar. And that's what we have right here. 10 minus negative 2.1676 times 4. That gives me 18.6704. Everybody okay? Scrolling up. And now we put those values in for the regression formula. Those B1 times X plus B0. Sorry, I want to make sure everybody can copy before I scroll up. Are you done with step 1? All right, so here's our answer right here. MATLAB normally, if I remember correctly, for you guys' application, they have a box. And one box would be sitting in front of X, and the other box would be behind the plus sign. So you just put your values in accordingly. Once again, pay attention to how many decimal places they want. And then here, I was just reemphasizing that Okay, these two values can be in different positions, but that 2.1676 has to be attached to x still, and it still has to be negative. So if anything's negative, it needs to stay negative. Whatever's positive needs to stay positive, and the number that's attached to x needs to stay attached to x, and it will still be the same equation. So it's not really about putting this one in front and that one, in the back, but just remembering that B1 needs to be attached to x, and B0 is the other value. Any questions? Any questions? Not sure what you mean by that. You just put regression calculations. Oh, you're talking about as far as finding B1 and B0? Okay, yeah, you would just put in the calculator. Yep. Unless you want to do it by hand, feel free. All right. So let's see. Before we, yeah, calculator would be easier. So, all right. So we have this and this. So this is what I'm going to do. That's an hour. So we've been good. I'm going to pause right here, and we will do this example next class, and then do 4.3 as well. 4.3 is very short, so I'm trying to give us some decent content for next class as well. So we'll finish this section off next class. We'll remember I told you you'll get your information in two different ways when it comes to calculating the regression line. This first one, they gave us the pieces to the formula. And this next one, they just give us the data set. We're going to go back to the club head speed. We're going to use that data set to create a regression line by using the app. And then we'll, perform these tasks right here. So we'll do that next class. And then, like I said, knock out 4.3. And then that'll be it for chapter 4. And we'll talk about how we're going to move going forward. So before we close out today, any questions? Any questions? Any questions? All right. Okay. So you guys have a good one. Be safe. Don't let me forget. This is where we start. I put an arrow there, so that'll probably remind me. But other than that, you guys have a great one. Be safe, and I will see you on next class. Thank you. Thank you. Have a good one. You do the same. Take care. Thank you. Take care. Take care. Have a good one.